Hi everyone, welcome to another video for research design and analysis. This is the second in our series of videos on the t-statistic, and I want to talk in detail about using t-statistics to conduct null hypothesis significance tests. So as a reminder, our observed t-value that we calculate in the sample is based on the distance between the mean that we observe and some hypothetical mean under the null hypothesis. And then we want to look at the distance between those two means in units of standard error. With the idea being, right, that if we assume, for instance, that the true mean is 0 and the x value, right, or the mean that we observe is 4 standard errors away, that's unlikely, right, given the mean that we hypothesized. Whereas if it's relatively close, right, for instance, we expect most sample means to fall within 1 standard error of the population mean. So if this t-statistic is only about 1, then that's not especially likely. Or sorry, I should say that's not especially unlikely under the null hypothesis, and in fact, that's a mean we would expect to get pretty frequently, right? So again, these factors of the effect size, the sample size, and the variance rotate about this fulcrum, right, to determine whether we think that the null hypothesis should be rejected, or if we think that the null hypothesis is pretty compatible with the data that we observed. So there are different examples of hypothesis tests, right? So under kind of like a more conventional one we might go through on a daily basis, I might have a null hypothesis that my oven is off, but then the alternative hypothesis is that my oven is not off, right? And what evidence would I need in order to reject the null hypothesis that my oven is in fact off? Similarly, I might have a hypothesis that freshman kinesiology students have a higher IQ than the general population, and this would be a good example of a non-zero null hypothesis test, because intelligence tests, right, by design have a population mean of 100. So my null hypothesis in this situation might be that the mean is equal to 100. And then my alternative hypothesis would be that the mean is not equal to 100. So in this case, I'd be interested in how close my sample mean is to 100 in units of standard deviation rather than how close my sample mean is to 0. And then, like as one we might have in a more, kind of common scientific study, we might ask, for instance, does mucimol act as an agonist of GABA receptors in the brain? And we could then say, well, my null hypothesis is that my mice who receive the mucimol, right, will have an equal mean in terms of number of GABA receptors to the control mice who received a placebo. So we could say that the mu of the treatment group is equal to the mu of the control group. The other way we could write this is that the difference between the means is equal to 0. So this would be a null hypothesis test assuming 0 difference. And the alternative hypothesis would be that those two means are unequal. And in all of these situations, right, we can conduct a null hypothesis test because we will determine what the null hypothesis is, and then we will say, what should our distribution of sample statistics look like, assuming that null hypothesis were true? So let's dig down on that a little bit and talk about, well, what is the null hypothesis? And I think it's a little bit unfortunate because there's some linguistic confusion here. Obviously in kind of common English usage, null means that it is 0, but in statistical terms, we don't always have a null hypothesis that assumes 0. It often assumes 0, but it doesn't have to. So I would encourage you to think about it maybe this way, is that the null hypothesis is the hypothesis to be nullified, right? We are setting something up in order to see how compatible our data are with those assumptions. And then if the data aren't compatible, something in our assumptions must be incorrect. So that's the null hypothesis test involves making a set of assumptions. And actually, I could probably word this better because those assumptions as a set are actually our statistical model. And the null hypothesis is one of the things that goes into that set of assumptions. So for instance, we would assume that the true mean in the population is 0. What other assumptions would be that sampling variability is the only factor operating on our data. We'd assume that we're all taking samples of the same size, right? There's a lot of things that kind of go into that statistical model. But in general, if our data strongly conflict with these assumptions, then we're going to reject the null hypothesis. And this is important because if your data disagree with your statistical model, it could actually be that one of the other assumptions is wrong, not necessarily that the null hypothesis is wrong. But we'll have future videos where we talk about, kind of checking those assumptions and going into those assumptions in more detail. But assuming that all of our other assumptions hold and the data that we observe are incompatible with the statistical model, then we're going to reject the null hypothesis and say the null hypothesis is not a likely explanation of these data. So what is the null hypothesis then, right? And like I said, often we make an assumption that there is no effect. So we might assume that the true mean under the null hypothesis is 0. And then we're going to assume that there's a distribution of sample means, which might look something like this. And it's centered on 0, right? Which is the true mean that we're assuming. Now, this is where the central limit theorem, right, bringing that back in, is really key. Because under the central limit theorem, it doesn't matter what the actual distribution of scores in the population look like. As long as we're making hypotheses about sample means, then we know that this distribution should be normal, right, at extremely high n, or that it should at least be approximately normal and follow the t distribution, right, at different degrees of freedom. So that's the beautiful thing about the central limit theorem, is that as long as we're making hypotheses about the sample mean, we can have a really robust and valid assumption about what this distribution of sample means should look like under the null hypothesis. So again, I do want to point out that we don't have to assume the true mean is 0. We've often used IQ as an example, right, where we talk about the population mean being 100. But often we're doing a null hypothesis test against a value of 0. There's another branch of hypothesis tests that are referred to as minimal effects tests that assume that the true mean is a meaningful non-zero value. So for instance, let's assume we wanted to see if people's reductions in pain following a treatment were statistically different than 0, right? Well, that might not actually be an interesting question, because we could say, you had a non-zero reduction in pain. But how big of a reduction in pain is clinically meaningful? If it's like 3 points on the scale, then having a reduction of 1 point isn't actually helpful, even though it's different from 0, right? So under a minimal effects test, we might say, rather than was it different from 0, we might say, was it different from some clinically meaningful value or threshold, right? So again, we don't necessarily have to assume 0 here, but by convention, we often do, because that will do a lot of work for us. So the null hypothesis significance test then, right, is how we can take this null distribution and make an inference about it given the data that we observe. So the null hypothesis significance test involves calculating the p-value, or the probability, of observing our sample mean as extreme or more extreme under the null hypothesis. So assuming that the null hypothesis is true, right? What is the probability of observing data that extreme or more extreme? So our null hypothesis in this situation is that mu is equal to 0, right? And you can see this kind of fanning out in either direction under our sample distribution. Our alternative hypothesis would be then that mu does not equal 0. And the question then becomes, where do we draw the threshold for when we would reject this null hypothesis, right? And say, well, we don't think that the null hypothesis is a great explanation of these data, and maybe the alternative hypothesis is actually a better explanation. So setting up something like this, where we're drawing these thresholds on both the positive and the negative direction, would be a two-sided hypothesis test, because we're interested in any sample means that show up over here, and we're interested in any sample means that show up over here. Now, alternatively, if we have a strong reason for doing so, we can draw these thresholds in a directional way. And you know, not necessarily test both sides at once, but we could say, okay, now let's, for a one-sided hypothesis test, we'll assume that mu is less than or equal to 0, and then we're interested in whether or not our sample mean crosses the threshold in this positive direction over here. In a complementary sense, we can also do the opposite and assume that mu is greater than or equal to 0, and then we're really only interested in if our sample mean crosses the threshold in the negative direction over here. So these are perfectly valid tests that you can conduct. These are called one-sided or directional hypothesis tests. And the main issue you face with doing these versus doing a two-sided test is you need a really strong rationale for why you only want to look at, you know, the distribution in one direction, as opposed to our two-sided test where we're interested in both tails of this distribution. So when we call this a significance test, you know, what makes a result statistically significant? So significance is an often abused word, for one thing, in the applied sciences. And it really is just a shorthand for, is something statistically interesting? It has nothing to do with whether or not an effect is real, right? It's unrelated to capital T truth. It just says, is what we observed interesting given our model under the null hypothesis? So let's say that this is our null distribution, and I observe a sample mean of 0.1. Is that statistically interesting or unusual given the null distribution? And no, not really. Under the null hypothesis, right, like what we're seeing in the red curve here, a mean of 0.1 is well within the bounds of what we would expect due to sampling variability alone. Now, if we change that and we say, well, what about a mean of 4? Well, okay, that's unusual given the null distribution. It could certainly still happen, right? A mean of 4 can arise in this distribution. The probability of it arising, though, is very, very small. So in this case, under the null hypothesis, a mean value of 4 is unlikely to arise, and we would probably reject the null hypothesis as a good explanation of these data. Again, it could technically happen under the null hypothesis, but it's so unlikely to happen that we think maybe there's something systematic going on rather than that these results arose due to sampling variability alone. Let's consider something more moderate now. What about a mean of 2? Is this statistically unlikely under the null distribution? Well, this is harder to say because under the null hypothesis, a 2 is unlikely, right? But it's not as unlikely as a 4. So how unlikely does something need to be before we would reject the null hypothesis? And this is where the idea of a significance threshold comes in. So a significance threshold, right, reflects what we would call the type 1 or the false positive error rate. And we write in statistics, we denote this with the Greek symbol alpha. So in practice, we're often going to set alpha to 5% or 0.05. And what that means is, under the null distribution, we're going to say that the upper 97.5 percentile and the bottom 2.5 percentile define what we think of as statistically interesting. So any scores that fall in that middle 95%, right, shown as kind of gray sample means down here, are not statistically significant. And all that means is they could have arisen due to sampling variability under our null distribution 95% of the time. Now, some of them might get very close to that threshold, right? But if it falls below that threshold, we would say it is not statistically significant. And we'll talk a little bit more about what that means and how to interpret that in later modules. But for now, let's just think about crossing that threshold, right? And then we get means that we say are statistically interesting on the more extreme side, right? So if you fall in the lower 2.5 percentile or the upper 2.5 percentile, combined then, that's 5% of the time we're going to be rejecting the null hypothesis. So the nice thing about setting these significance thresholds is that under the null distribution, we will only get false positives, right, 5% of the time. Which is to say that if the null is true, and we set this as our threshold for declaring an effect, and this is our threshold for declaring an effect, we're only going to make the wrong decision 5% of the time. So there are a lot of issues and complications that go into null hypothesis significance tests, and we're going to talk about some of those today. But their real strength is type 1 error control, right? And we can reduce the number of false positives that we're making if we kind of cleave to this decision of saying, well, this is our threshold for statistical significance. Anything above that, we're going to say is statistically interesting. Anything below that, we're going to say is not necessarily statistically interesting. Now, it's important to emphasize that that doesn't mean there's no effect here, right? If I observe this sample mean, there is a negative mean that I observed in my sample. Just because its p-value doesn't cross the significance threshold doesn't mean there's no effect. It just means I didn't have enough evidence in terms of where I set my alpha level to declare that effect was statistically interesting. So that's very important, and we're going to talk about that later. But just because something is not statistically significant does not mean there is no effect, and that's a very common misinterpretation of statistical significance. Okay, so let's think about this type 1 error rate in a little more detail then. So by changing the alpha level, we can change the threshold for what we consider statistically interesting. Now, this is going to have costs, right? Because if I make it harder to declare something statistically interesting, that means I'm making it harder to declare a research finding. Which might mean that if I don't say that it's statistically interesting, maybe I don't go on to do another experiment in this area, or maybe somebody else doesn't, right? And these things can potentially then have an influence on clinical practice. Not that they should, because we should never conflate a single p-value with what is clinically meaningful or what is important. But one of the downstream effects of kind of setting these thresholds is it kind of guides and steers research, because we're going to declare something statistically interesting, and then if it's below that threshold, it's an equivocal result. If it's past that threshold, we'll declare it statistically significant, and that kind of suggests that it merits looking into it further. So why then would we, for instance, set alpha at 0.05 and not 0.001? Which is to say, if type 1 errors are bad, why not reduce the risk of type 1 errors, to an even greater extent? Why not make this threshold much more extreme? And the answer to that is that different types of errors trade off. And in the same way that we have type 1 errors, right, we also have type 2 errors. And we can see this more clearly if we think about our decision regarding our significance criterion, right, rejecting the null hypothesis or failing to reject the null hypothesis, contrasted against, reality, where we could say the null is false or the null is true. Now, if we reject the null when it's false, that's a true positive. That is the correct thing to do in that situation. We've declared a research finding when there really is one. Similarly, if we fail to reject the null when the null is true, right, then that's a true negative, right? We've correctly said, I don't feel comfortable calling this a research finding. I'm not going to make any kind of declarations about the data that I observed in my sample and try to generalize them back to the population. That would be a true negative in that situation. But, right, like we said, we can make false positives, which is, the kind of the way we might talk about this in common language is that this is a false alarm. We reject the null hypothesis when the null is actually true. And like we said, setting the alpha level at 0.05 means we can say 5% of the time is what we're going to get false positives, assuming that the null hypothesis is true. So we can control kind of the size of this box by setting alpha. But the reason why we don't necessarily set that to, one extreme value or another is that if we move that threshold, the other thing we're going to be affecting is the rate of false negatives, which is when we fail to reject the null, when in fact we probably should. So where we set this alpha criterion really matters, right? So again, in reality, the null might be either true or false, and we're going to make a decision based on where we set this alpha threshold. So when the null is true, we will only falsely reject the null 5% of the time if we set alpha equal to 5%. So what if we set a more liberal criterion and we move that in a different direction? So if we set alpha equal to 0.15, right, now we're saying a wider range of sample statistics will be treated as, evidence for rejecting the null. We're moving our threshold for what constitutes a research, finding, kind of in quotes. So the rejection rate is going to go up, right? We're going to declare more things research findings because now we're rejecting the null 3 times as often as we were before. But the problem is the false positive rate is going to go up as well. So we're missing fewer potential results, but we're also declaring more false positives. And if we move that in a more conservative direction, right, the reverse is going to be true. So if we set alpha equal to 0.001, right, now we're declaring fewer things as research findings, right? We're rejecting the null less often. And that means we're going to have fewer false positives in those situations when the null is true. But then what's going to happen is we're potentially going to increase the rate of false negatives, right? So because we're saying we're setting a higher bar for what we think is statistically interesting, we might miss out on some effects that are actually there. Because as these false positives go down, then the rate of false negatives necessarily goes up because these two things are interrelated. So we can actually think about 2 different types of errors that we're making here. One is a type 1 error, right, when we get a false positive. And by default, we'll usually set the alpha level equal to 0.05 to control the probability of making a type 1 error. But the complementary probability that we have to be worried about is the probability of making a type 2 error, right, which is a false negative error. And we'll get more into type 2 errors when we talk about the issue of statistical power. But the thing I want to remind you of right now is that these 2 things trade off. And so we can't just set alpha to be super, super low and not expect that to have consequences. And we can't expect to set alpha to be super, super high and not expect that to have consequences. And so what it really comes down to in terms of what's an appropriate level for type 1 and type 2 errors, and that's going to determine what we want to set the beta probability to be and what we want to set the alpha probability to be. So the null hypothesis test, again, is only one of many statistical tools, right? But it's very useful, right? And its particular strength is control of these type 1 errors. Because if we don't have to really know an awful lot about the state of the world or make a lot of other assumptions in order to set alpha at 0.05 and say, okay, assuming then that we have this null hypothesis, this is our null distribution, we're going to separate the extreme 5% from the middle 95%, and we can control the type 1 error rate. So other types of statistical analyses are very informative, but they require more assumptions about the state of the world. And that's not to say that those things are bad, right? Because nothing is wrong with assumptions. Assumptions aren't bad. Bad assumptions are bad, right? So as long as our assumptions are defensible and appropriate, then having additional assumptions built into our statistical model isn't going to be a problem. We're teaching you about the null hypothesis significance test because it kind of does a lot of the legwork in day-to-day scientific research. But I just want to emphasize again that there are a whole host of other things that you might be interested in testing that are not null hypothesis significance tests. And there are methods for those things that exist, but this is a useful place to start.